Okay, here we are with this problem right here, where we've got a right triangle that passes through the point 1, 2 and intercepts with vertices on the y and the x-axis. And we're supposed to write the length of the hypotenuse as a function of x. Now I'm going to take this to Desmos first, just so you can see what's happening here. Here's the triangle. Here's the point 1, 2. And as I slide this x-coordinate to the right, this x-intercept to the right, the length of that hypotenuse changes. And here's a table that has the length of the hypotenuse in it. So it looks like when x is 2, the length of the hypotenuse is 4.47, and as I keep increasing x sub 1, the hypotenuse keeps getting longer and longer until it's, well, it's undefined, because I only let x sub 1, the function, be defined from 1 to 10. But it looks, so the question is, how do we come up with this formula for the length of the hypotenuse? That's what we're going to work on next. And so let's stop sharing for a second. Come back to page 2, and this distance right here, from here to here, is x. In this case I have a specific number here, 4, but in general that distance is x. This distance is y. The length of that hypotenuse will be the square root of x squared plus y squared by the Pythagorean theorem. And what you want to get used to in these problems, related rate problems or optimization problems where you have a right triangle, is start looking for similar triangles. So this, the big triangle here, is similar to this triangle here, where we have the vertical side right here. That small triangle is similar to the big triangle by angle. We've got two right angles and they both share this angle. And of course these angles are also congruent because we've got two parallel lines cut by a transversal. Alright, so the length of the hypotenuse is, in terms of x and y, is the square root of x squared plus y squared. But we're supposed to get that length in terms of x only. So here's the key. In these similar triangles, this y side is to this long side, y is to x, as this green dotted line is to this distance. Now how can we represent those distances? Well, this distance is always 2, because that's the y coordinate of the point that we're always going through. This distance right here is the total distance, x. Take away this little distance right here, which is a 1, because we're going out to the point 1, 2. So this distance right here is x take away 1. So y is to x in the big triangle, as 2 is to x minus 1. And if I solve for y, I get 2x over x minus 1. So that's what this distance is right here in terms of x. 2x over x minus 1. So the hypotenuse, the formula for the length of the hypotenuse in terms of x is this side squared plus this side squared, the square root of that. And that's what this is right here. There's your formula. And when I graph that function, that's what we mean for part 2. So this is the answer to part 1 right here. This is the answer to part B. It looks like when we graph the length of the hypotenuse function, that the minimum value for the length of the hypotenuse occurs at 2.587 to 3 decimal places. So the graph, you're just supposed to pick a graph, multiple choice. The question is, how do we come up with that 2.587? Can we do it? Well, if we go to board 3, L of x equals, this gets really ugly, 2x over x minus 1, the quantity squared, plus x squared to the 1/2 power. That's the length of the hypotenuse function in terms of x. And we want to find out when that's a minimum. So we have to find the derivative. Well, this is going to get ugly. I mean really ugly. Okay. Well, there's a lot of ways to do it. We could simplify what's inside here and then take the derivative, or we can leave it just like it is. I'm going to leave it just like it is, and I'm not going to go through every step. But if we take this 1/2 down front, repeat what's inside the radical. Whoops, this should be the whole thing squared, sorry. So I can replace that with 4x squared. X minus 1, the quantity squared. Plus x squared, that's what's inside the radical. That all goes to the 1/2 power, reduced by 1, so negative 1/2. And now we have to use the chain rule. And that's the derivative of the inside. For this first term, we have to use the quotient rule. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which will be 2 times x minus 1, all over the denominator squared, plus I still have the derivative of this term. So this block over here is the result of using the chain rule. And we want to know when this mess equals 0. Well, I can write this as 1 over 2 times this whole thing to the 1/2 power times this thing. And when I simplify that, whoa, what am I going to do? Well, I'm going to factor out this x minus 1 in the numerator of the first fraction and get 8x times x minus 1. I factor out an x minus 1, so I get minus 8x squared. I still have all over x minus 1 to the 4th power. And I still have this plus 2x. And if you picture multiplying all these together as like one big fraction. By the way, this x minus 1 cancels out with here and gives me x minus 1, the quantity cubed. But I've got 1 over 2 times the square root of this mess, I'm not going to write it again, times, I've got, well, what have I got? 8x squared minus 8x minus 8x squared This is over x minus 1, the quantity cubed. And I still have this plus 2x sitting out here. Wow. When will this equal 0? Well, it's going to equal 0. Ooh, well, maybe I better do a little bit more work here. This problem is pretty bad, pretty horrible. Edit, copy. Go to board 3. Finish simplifying. This part, in the end, we're going to ignore because this part will never equal 0. See, I'm going to go equal 0, and this part will never equal 0 because there's no variables in the numerator. This part will equal 0, and that's what I want to work on. 8x squared minus 8x squared is minus 8x over x minus 1, the quantity cubed, plus 2x. When does that equal 0? Well, I'll multiply everything by x minus 1, the quantity cubed. I get minus 8x plus 2x times x minus 1, the quantity cubed, still equals 0. Now, how am I going to solve this for x? Well, I'm going to get like x to the 4th formula. And this is where you probably have to use a graphing calculator. I multiplied all this stuff together. I cubed x minus 1, distributed the 2x, added in the negative 8x, and then I graphed. Whoop, I got to share my screen again. I graphed this function right here, which is what I get when I simplified all that mess, and then divided by 2x, I think. And if I graph that function, when does it equal 0? There it is, 2.587. That's when the first derivative equals 0, when x is 2.587, and that's why this 2.587 produces a minimum value. What a problem. Okay, I'm going to stop sharing, go back to board 1. So this was L equals the square root of 2x over x minus 1, the quantity squared, plus x squared, for x greater than 1. For the second problem, you want to, on a graphing calculator, graph this function right here. Y equals this. And this is the picture you're going to get right here. And at that minimum value, or the x value that creates that relative minimum, you will get the minimum length of the hypotenuse. And for this problem right here, round your answer to 3 decimal places. Okay, edit, copy. The answer to this problem right here, the minimum value occurs when x is 2.587. Finding that using the first derivative, relative minimum and maximums, is quite tedious. The last problem of this section was part C, I guess. New rectangular snip. Whoop. Yeah. 6. So it says find the vertices of the triangle such that its area is a minimum. Order your answers from smallest to largest x. Okay, I'm going to pause the video. Okay, let's finish up here. So for this problem, we're supposed to find the value of x that minimizes the area of this same triangle. So this is still x. This is still 2x over x minus 1, which we found this value by creating similar triangles. And the area of a triangle is 1/2 the base times the height, or 1/2 the height times the base. So here's a formula for the area of this triangle, depending on x. If I find a prime using the quotient rule, denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is going to be 1 over x minus 1, the quantity squared. So there's your final derivative. We want to know when that equals 0. It equals 0 when the numerator is 0, which is when x equals 0 or x equals 2, but we reject x equals 0 because we're dealing with a triangle where we said the x value had to be greater than 1. So we get x equals 2. And when x is 2, if I put 2 in for x in the formula for y, put a 2 right here, 2 times 2 is 4, 2 minus 1 is 1, 4 over 1 is 4, so the y value is 4. Now, the question is, what are the vertices of the triangle? Well, this is going to be 0, 0. This is going to be 0, 4. And this is going to be 2, 0. So I guess they're looking for 0, 0, 0, 0, 0, 4, and 2, 0. If I go back to Desmos, actually I don't need to share my screen. Back to Desmos, here's the a of x function, x squared over x minus 1, and here's a little table showing the possible values. And this is actually the graph of a of x. So that's the minimum value right there when x is 2, y is 4. And you see that the minimum area is also 4, 2 by 4. If I slide this area this way, the area gets bigger and bigger. So when x is 2, we get the smallest y value, or smallest area. And I actually meant to put x sub 1 in here. And so you can see if I slide x sub 1, the area gets bigger and bigger. Watch that x sub 1 there. Right now it's at 8. It just keeps getting bigger and bigger. If I slide it back towards a 2, that's when the triangle has the smallest area, an area of 4. Okay? Okay, that was a complicated problem, maybe a little harder than, it jumped right from fairly simple optimization problems to a really hard one. So I'm going to post this video and send you the link.